Okay, you try to open your microphone and talk something.
Can you hear me?
Yes, I can hear you, but can you hear me also? Hello, Mr. Daulat Khan, can you hear my voice?
You can send the link.
Daulat? Hello, Daulat?
Okay.
Hello, Daulat? Can you hear me? Hello? Daulat?
गई ना
Daulat? Daulat?
เราจะทำอันนี้เมื่อไหร่พูดสด
ไอ้ตรงที่แบบทำไมต้องมาในปัญหาตรงนี้ขึ้นนะ
ต้องเลือก
Hello?
วันนี้ได้ไหม
ไม่ถึง
You can hear me? Good.
เชื่อมโยงระหว่างปฏิเอเจน
Daulat, sama awas dari sini.
หรือคนนะเชื่อไม่ได้อะไรยิ่งโหดประมาณ2 อันข้างล่างเป็นหมด
Sakib.
Sama awas dari sini.
Okay.
Hello, sama awas dari sini.
Rajiv Kumar and Rajiv.
Wait for 2 minutes.
จะเข้าฟังอันนี้ไม่เข้าฟังอันนี้เนาะ
Hello, Jabir.
What?
Give your hands.
Hello.
Yeah.
Hello and welcome to the lab presentations seminar series for this second semester 2022 session. Today the presentation will be holding on Mondays and Wednesdays and 1:30 from 1:30 to 3 p.m. Today's presentation is by Daulat Khan and Sakib Murtada, and the topic for the presentation is heat transfer analysis of zinc, aluminum based standard hybrid nanofluid fractional model by infinite difference approach. I hope we'll all enjoy and learn a lot from the presentation. Now we can start.
Okay. Can we start?
दोला तो
Are you, Sakib,
आवाज
can you hear
resumes?
me? Yes.
Okay.
Can you hear me?
Yes, I can hear you.
Okay. Adam, can we start? Okay. Good afternoon and welcome all of you in your group presentation. And this is me, Mr. Dola Khan, and my group presenter, Mr. Sakib Murtaza, and our mentor, Professor Dr. Pomkumam. The title of today's presentation is Heat Transfer Analysis of Zinc Oxide, Aluminum Oxide, and Titanium Oxide based ternary hybrid nanofluid, a fractional model by finite difference approach. This is the research background. First of all, we will discuss some basic background of the our research, and after that, we have some research methodology, and then we discuss the mathematical modeling of our problem, and after that, we apply the general fractal definition on our model, and we generalize our model, and after that, we discretization of the model for the solution through finite difference scheme. And after that, we have some graphical and tabular analysis. Last, we conclude our remark. As we discussed from the very basic, that is fluid. Fluid basically a material that has no fixed shape and deform under applied stress. We have main two types of fluid, that is Newtonian fluid and non-Newtonian fluid. Those fluid which obey Newton's law of viscosity is known as Newtonian fluid, and which do not obey the Newton law of viscosity are known as non-Newtonian fluid.
Sorry,
Newton law of-
Dola. Can you
Yeah,
open your camera?
Okay,
Thank you.
thank you. Okay, the Newton law of viscosity state that when the shear stress is directly proportional to the deformation rate. Water, air, and kerosene oil are the example of Newtonian fluid, while the oil, honey, and blood are the example of non-Newtonian fluid. We have some properties of the fluid. That is, the first one is compressible fluid. Those fluid which have variable density. When we apply some external shear stress, and it can be compressor is known as a compressible fluid, and which we and those fluid which have no constant density, which have constant density and which cannot be compressible are known as incompressible fluid. Viscosity actually is the thermal property of the fluid. It is the fractional forces resulting due to the interaction between the layer of molecules. Okay, we have many types of fluid. Some of them are steady fluid. In the steady flow, the velocity of the fluid at any point is constant with respect to time. It's mean it does not depend on time. And in the other hand, unsteady fluid exists whenever the velocity of the fluid at any point change with respect to time. It's mean this flow is depend on time. And after that, turbulent flow. The turbulent flow is the extreme kind of unsteady flow. It's mean it's totally change with extremely change with respect to time. Also, we take some heat transfer. So we must know about the heat transfer. Heat transfer is the exchange of heat from one object to another object due to the temperature difference. There are main three types, three ways. The first one is conduction. Conduction is that type of heat transfer which transfer the heat through material. And the second one is convection, and this type of heat transfer is occur in fluid. And the third one is radiation, which heat transfer is occur by waves. In many fluid dynamic, many researchers are working fluid without nanoparticle, but it have a problem to enhance the thermal conductivity. For this purpose, we have some solid particle which has a high thermal conductivity and which can be used to enhance the thermal conductivity. For this purpose, initially Maxwell tried make microparticles in a base fluid, and it create a microfluid, but this is failed because due to the sedimentation and collaging and blockage of narrow channel. After that, in 1995, Choi worked in Argonne National Laboratory at USA, and he invented the nanomaterial size particle and added in a base fluid, and that's become a nanofluid. And this nanofluid is used to enhance the thermal conductivity of fluid. This is the preparation of a nano fluid, which we add some nano particle in a base fluid, and we create some nanofluid. These are the main application of nanofluid, which can be used industrial cooling application, nuclear reactor for cooling purpose, biomedical application for drug delivery, and so on, and also in computer and mobile accessory, and used for automotive, for in radiator, and also some agriculture application. But after that, nanofluid, the researcher work and get some modified nanofluid, that is hybrid nanofluid. Actually, hybrid nanofluid is the modified version of the nanofluid, in which we insert two or more than two nanoparticle at the same time in a single base fluid, and which become a hybrid nanofluid. So initially, researchers are try two nanoparticle, but nowadays the researchers are trying to enhance more thermal conductivity. For this purpose, he tried the trihybrid nanofluid. So trihybrid nanofluid is actually a modified version of the hybrid nanofluid, in which we can add three different type of nanoparticle in a single base fluid, and which can prepare a trihybrid nanofluid. This is the modified form of the initially hybrid nanofluid. We use for generalization fractional model of our problem. So we must know about the fractional derivatives. Initially, on 30th of September 1960, Al Hospital wrote a letter to Leibniz. He asked a question about the power of the derivative. What will happen when the power of the derivative become 1/2 and fractional? Leibniz response that it is a paradox, and from one day, maybe some useful consequence will be drawn. And the communication between the L Hospital and Leibniz had given a birth to the fractional calculus. And this is the initial conversation between these. And we say that this is the birth of our fractional calculus. After that, many researchers working on the different fractional derivative, and some of these are Riemann-Lebedev fractional derivative, Caputo fractional derivative, Caputo-Fabrizio fractional derivative, Artangano-Bellino fractional derivative, and all of these are used in different field of research. We also use in fluid as well as in many other field of research. But recently we tried to factor fractional derivative, which is the most new fractional derivative which is used by researcher. This is the significance of our study, that the result obtained from this research will help to enhance the knowledge of fractional in model in fluid dynamics, and also the nanofluid flow, and especially the trihybrid nanofluid flow. And a base of complex non-linear flow problem recurrently taking place in engineering and applied science. So this type of study can help to engineer and scientists and understanding physically trend of feature of various nanofluid flow, that is nanofluid, hybrid, and trihybrid. And fractal fractional model will provide deeper study about the rheology of fluid flow as compared to the fractional and classical mean. It means that the fractal fractional model will help to provide the more realistic phenomena, more realistic model to the classical and simple fractional model. This is the methodology of our problem that first of all, we propose some problem through mathematical modeling, which consists of initial and boundary condition, and we have some dimension governing PDs. First of all, we apply the non-dimensionalization process. For this purpose, we use Buckingham Pi theorem, and through which we can get some non-dimensional variable, and we use for non-dimensionalization. After that, we get some dimensionless initial condition, dimensionless governing PDs, and dimensionless boundary condition. And after that, we apply the fractal fractional approach to this model, and we make our dimensionless governing equation to a generalized fractal fractional model. And after that, the solution. Actually, this model cannot be solved exactly, so we use the numerical solution by finite difference scheme, and then we plot the different phenomena, different physical parameters, and last conclusion. Now I invite Sakib Murtaza to present from this slide.
Hello, everyone. My voice is clear?
Yes, we can hear you.
Okay. Good afternoon, everyone. As you know, my name is Sakib, and I am here to present my group presentation. So let me start from the geometrical configuration of the flow phenomena. In this geometry, we have considered an unstudied fractal fractional order model of nonlinear trihybrid nanofluid and open bounded channel of a length L. Furthermore, the impact of thermal radiation, Joule heating, and viscous dissipation has also been considered in this study. Hello?
Yes, I can.
My voice is clear?
Yes, yes.
Okay, sorry for interruptions. Furthermore, please go back to the geometry. Please go back to, yes, this one. The impact of thermal radiation and Joule heating and viscous dissipation has also been considered in this study. The magnetic field of a strength B0 has transversely applied to the fluid flow. At the beginning of the analysis, both the channel and the fluid are assumed at rest, but after T is equal to 0 plus or after T greater than 0, the temperature and the concentration of the fluid rise to time-dependent concentration and temperature of the fluid. And all of these things you can see in this geometry. Please next. These are the mathematical models, system of phenomena. The first one is equation is the momentum equations, which we derive or develop from the second law of momentum. The second one is heat equations, which we derive from the heat law of conductions. And the third one we have developed from the Fick's law. So all these three equations will be solved in this group presentations. Next, please. These are the associated boundary conditions. At the left plate, we have no motions, but at the right plate, we have some sinusoidal oscillations with the sign omega t. And also we have variable temperature and variable concentration. These are the thermophysical properties of the base fluid and the three different nanoparticles. The base fluid has been considered is DW, that is distilled water. And the particles are aluminum dioxide, titanium, and zinc oxides. And all these are the thermophysical properties which are obtained experimentally. To make our system dimensionless, we will use the dimensionless variables that are given in equation 5. So incorporate all these equations, we will get our momentum equation in the form of equation 6. Heat equation will be in the form of equation 7. And next, please. Next, please.
Yeah, we are already in next slide.
So I didn't see anything here. Okay. The equation 8 is actually the concentration equation in dimensionless form, along with the associated initial and boundary conditions that are given in equation 9. These are some constants which we have been obtained during the dimensionalization process. These are also some constants. Okay, now we will generalize our model by using the fractal fractional operator of Caputo-Fabrizio with non-singular kernel. So we will just replace the time derivative, ordinary time derivative with the fractal fractional derivative, and we will get equation 10, 11, and 12. The fractal fractional operator has been explained here in equation 13. And equation 14 and 15 are the discretization of fractal fractional operator, because we are going to solve our problem with the numerical scheme, that is finite difference scheme. So these are the discretization of the fractal fractional order. This is the first order derivative discretization with finite difference scheme. And equation 17 is actually the second order discretizations. Now, using the discretizations defined in equations 14, 17, the generalized, so the momentum equation will take form of equation 18. This is heat equation in general in discretized form. And this one is concentration equation in a discretized form. Now we will plot the graphs in response to the embedded parameters. In these sections, we will discuss the graphs with physical arguments. Figure 2 actually described, plotted for the comparison of fractal, fractional, and classical model. The fractal fractional model is more general than any fractional and classical model. Because one can easily deduce the fractional model and classical model from it by fixing its parameter according to the situation. Fractal fractional model or fractional model is actually used to describe the memory effect of the fluid phenomena, and it is more close to the real world problems. Fractal fractional model give us a variety of solutions and multiple integral curves, and the experimentalists can easily compare their field survey data with one of the best fitted curve. Figure 3 has been drawn for the impact of volume fraction of nanofluids, nanoparticles on the thermal profile. In all the models, temperature distribution shows an increasing trend in its behavior for increasing magnitude of volume fraction phi. This trend in the thermal profile is due to the advanced thermophysical property of the dispersed nanoparticles. The dispersed nanoparticles increase the thermophysical characteristic like specific heat capacity, density, concentration level, viscosity, etc. of regular distilled water. Therefore, the thermal performance of the water enhances and shows an increasing trend in the heat distribution. Figure 4 has been drawn to show the impact of Eckert numbers on the thermal field. The thermal field show enhancement in response to greater value of KMUTT numbers. KMUTT number shows the relationship between the kinetic energy of the boundary layer and X enthalpy difference. As the magnitude of EC rising, the heat start transferring from the plate to the fluid. And due to this, the dissipation of viscosity increase, and as a result, thermal field show enhancement in its profile. While on the other hand, we have impact of Joule heating parameter on the thermal field. A rise in the field of temperature can be noticed by increasing value of Joule heating. This variation in temperature field is due to the extra amount of energy reduced in the fluid by Lorentz forces. This extra amount of energy enhances the fluid temperature, and as a result, we receive a rise in the temperature field. The impact of Schmidt number has been drawn in figure 7. Figure depicts an increase in the concentration profile of the fluid against greater magnitude of Schmidt number. And this variation in the profile is due to increased viscous forces and concentration level of the particle, which causes to increase the concentration profile. Figure 6 shows the impact of volume friction on concentration profile. And from the figure, we can easily observe that concentration distribution decline when phi increases. When phi increases, viscosity of unary, binary, and ternary hybrid nanofluid arises, which decrease the mass distributions in all the cases. Figure 8 has been drawn to show the impact of permeability parameter K on the velocity profile. It is noticed that the K accelerate the velocity as by increasing value of K, mean improvement in the permeability, which reduces the resistive forces and as a result increase the fluid velocity. On the other hand, figure 9 has been drawn to show the impact of magnetic field on the velocity of the fluid, and we can show a decreasing trend in the profile of velocity. When the value of M increase, the Lorentz forces in the fluid act upon, and as a result, we have a decreased trend in the profile. In figure 10, we can see the impact of Grashof number on the velocity profile, an increasing trend in both the figure 10 and figure 11, where figure 11 has been drawn for the thermal Grashof number. In both the figure, we can see increasing trend in response to the greater magnitude of the GR and GM. And this is due to the buoyancy forces and concentration level. Both these parameters increase the buoyancy forces in the fluid, and as a result, we get increasing trend in the velocity profile. This bar chart has been drawn to check the impact of Nusselt number graphically. And you can see for the ternary nanofluids, we have greater Nusselt number in all the cases for the volume fraction 0.04. 0.04 mean percentage of the volume, the nanoparticle will be 4% as compared to the distilled water. Percentage enhancement in Nusselt number. Now the previous graph will be supported by these numerical tables, and you can see for all the nanoparticles we have used individually, and for the 0.04 we can see that 11% increase for the aluminum, 11.94% increase for the titanium, and 12.31% increase for the zinc oxide. If someone going to use in these three parameters, so zinc oxide will be the best choice in this case. Figure 4 has been drawn for the hybrid nanoparticles, and we can see that when the value of phi reached to 0.04, for aluminum and titanium, the percentage enhancement is 12.60. For aluminum and zinc, the percentage enhancement is 12.80. And for the titanium and zinc, the percentage enhancement is 13.23. This is when someone or experimentalists use all of these three particles at a time, So he or she will get 16.33%, which is best result in all of the cases. These are some concluding remarks which we have drawn from our solutions. That fractional operator give us a variety of results to best match the theoretical finding with the experimental survey. The fluid velocity increases for greater value of K, Gm, and Gr, while decrease for M. Considering the dispersion of nanoparticle individually, zinc oxide gives us 12.31. Please come to the concluding remarks. Aluminium oxide shows 11.39%, and titanium oxide give us 11.94% heat transfer enhancement. In binary hybrid nanofluid, the combination of aluminium and zinc enhances heat transfer up to 12.8, titanium and zinc enhances 13.23, and aluminium and titanium enhances 12.60 transfer rate. And in the last key point, we can see that ternary nanoparticles increase 16.33% when dispersed nanoparticles reach up to 4%. And we get the best result in all of the cases. These are some future directions. One can easily extend this model by considering different geometry, cylindrical, verticals. This is the researcher choice. By different boundary condition, we can also extend with different base fluid and nanoparticles, different non-Newtonian fluid models with fractional derivatives, and compare their results. And to connect these models with different engineering and biomedical applications, we can also extend this present model. Thank you.
Thank you for the wonderful presentation. Now for the audience, if you have any question, you can ask. Hello, can you hear me?
Yes, sir.
Okay, can you show the table for thermophysical properties?
This one.
Yes. Okay, I want to know that the value of thermal conductivity for these 3 nanoparticles is very much different. I mean, one is 40, one is 8 point something, and one is 1 point something. But when we see the table for the Nusselt number, the difference is almost very, very small. So how you see this?
Okay, very nice question from Dr. Talha. Here we don't have only one parameter, that is, you mentioned K, where we have also some different parameters like CP, like density, like volumetric expansions, and many more thermophysical property we have. So when the heat transfer increase or decrease, it depends on all these parameters simultaneously, not only on K. So therefore, we can see a minute difference between the heat transfer rate.
Oh, okay. Okay, can you show the dimensionless boundary conditions?
This one.
No, dimensionless, please. On page, slide 22.
Okay, I thought there is some mistake, but okay.
Thank you.
Okay. Okay, that's all from my side. Thank you.
Welcome.
Thank you, Dr. Kalina.